In this video, we're going to talk about the concept of linear programming. In this concept, we're going to probably use like graphing linear inequalities to kind of help us solve some real life example problems of minimizing and maximizing. Fundamental theorem of linear programming. If an optimal value for a linear programming problem exists, it occurs at a vertex of the region of feasible solutions. Solving a linear programming problem. Write all necessary constraints and the objective function. Graph the region of feasible solutions. That's going to be graphing the system of linear inequalities. Identify all the vertices or your corner points of the region of your linear inequalities. Find the value of the objective function at each vertex. The solution is given by the vertex producing the optimal value of the objective function. Here's a real life situation that we could look at to see how this actually works. The manufacturing process requires that oil refineries manufacture at least 2 gallons of gasoline for each gallon of fuel. To meet the winter demand for fuel oil, at least 3 million gallons per day must be produced. The demand for gasoline is no more than 6.4 million gallons per day. If the price of a gallon of gasoline is $2.90 per gallon and the price of fuel oil is $2.50 per gallon, how much of each should be produced to maximize revenue? Well, our objective function for this problem we can get from that last statement. We need to first say, okay, we're going to let X equal the number of millions of gallons of gas. Y can equal the number of millions of gallons of fuel oil. Okay? So if it says that if the price of gasoline is $2.90 per gallon, then our objective function is going to be 290 X, and then the price of fuel oil is $2.50 per gallon, so plus 250 Y. That is the objective function that we're going to try to maximize. We want to get the highest amount of revenue we can get. We have some constraints involved here, though. The first constraint, it says, is that the process requires that oil refineries manufacture at least 2 gallons of gasoline for each gallon of fuel oil. So in that statement, at least means, okay, the number of gas, number of gallons of gas, has got to be at least, so it's got to be greater than or equal to 2 times the amount of fuel oil. At least 2 gallons of gas for each gallon of fuel oil. So X has got to be greater than or equal to 2 times Y. So gas was the X, Y was the fuel oil. So yeah, the amount of gas has got to be either greater than or equal to, because it says at least 2 times the amount of fuel oil. So that's our first constraint. We'll call these our constraints. All right. To meet the winter demand for fuel oil, at least 3 million gallons per day must be produced. So at least 3 million per day. So for fuel oil, Y has got to be greater than or equal to 3. The demand for gasoline is no more than, so it's got to be this or less, 6.4 or less, no more than 6.4 million gallons per day. So we could say X has got to be equal to or less than 6.4. Now, we need to also take into consideration in this problem, we've got to produce at least some of each, fuel, oil, and gas. So we need to consider X and Y to be positive in this problem. Or X at least to be positive. Y's got to be greater than 3, so sure enough, X has got to be positive. Okay, so there are my constraints. Let's go over to the next page and graph these constraints. X greater than or equal to 2Y. Let's see. If we solve this a little differently, if I divide by 2, so 1/2 X. So Y is actually less than or equal to 1/2 X. So this line is like a slope of 1/2 over 2 up 1 over 2 up 1. And I can do that as much as I want to. So there is my line. Okay, and since it's less than that, we are talking about, let's see. Can't use the origin as a test point in this problem, so I'm going to use the point. How about we use the point 2, 4? I'll use the 2.24. So if I use the point 24, 2 times 4. It's false. So we're going to have to be graphing lower here. So we're going to graph on this side. All the points below. Okay, notice I'm keeping everything in the first quadrant. Okay, let's go back and look at our next constraint. Y is greater than or equal to 3. Y equals 3 we know is this line. And it's greater than, so that means it's everything above the line. So I'm not going to shade all that just yet because that could get too much going on here, but it's everything below the line. I'm sorry, everything above the line, Y equals 3. Got stuff going on with my graph here. I'm trying to keep it all neat and clean. It's a little bit hard to do. X has got to be less than or equal to 6.4. 6.4 would be about less than is going to be everything to the left of it. So actually what we have for our constraints here is going to be a little triangle right here. A little triangle right there. And the corner points of your triangle are going to be it's a little triangular region. The bottom one right there is going to be where your x coordinate is 6.4. If you know your equation, well, it's on that red line there, and 6.4, and then up to 3. The top region, corner point right there, is going to be also where x is 6.4. But it's where it intersects the blue line. And the blue line we know is y is equal to 1/2 x. So 1/2 of 6.4 would be the point 3.2. And then the other point we know has a y coordinate of 3. So it also intersects on the blue line as well. So if y is 3, we know x would be 6. So our maximum and minimum optimization points that we have here are the points 6.3, 6.43, and 6.43. 3.2. So this is a hard one because the little area of region where we were graphing is very hard to see, but it's a little triangular region. Okay, because remember don't forget about this. We were shading greater than 3 here, so it's going to be the stuff above the red line. So this little black triangle is where I'm talking about. All right. So now that we know our corner points, we can go back and plug those into the objective function and see what happens. So let's try the point 6,3. So if I use the point 6,3, the objective function will be 2.90 times 6 plus 250 times 3, which will give us a maximum revenue of $24.90. If we use the next point, 6.43. $2.90 times 6.4 plus 250 times 3. The revenue would be, using your calculator, 2.90 times 6.4 plus 2.50 times 3, 2606. Okay, and then the last one, let's see, the last point, 6.43.2. I'll come over here where I've got some room. 6.4, comma 3.2, 290 times 6.4 plus 2.50 times 3.2. Let's see what that gives us. We're trying to maximize the revenue, so we want the highest amount. 2.90 times 6.4 plus 2.50 times 3.2, 2656. So, of course, that's the bigger amount. So, if the price of gasoline is $2.90 per gallon and the price of fuel oil is $2.50 per gallon, how much of each should be produced to maximize the revenue? So there should be 6.4 million gallons of gasoline produced and 3.2 million